Carbocation rearrangement is a central phenomenon in organic chemistry. Understanding it is critical for practically any level of organic chemistry study, no matter how basic or advanced. It may seem intimidating at first, but it is unavoidable, and without a solid knowledge of what is happening and why it happens, you may find yourself swamped in the details of a later reaction. Here we see an organic chemical rearranging. It's a hexyl carbocation. Notice how the positive charge, the green plus, jumps from carbon to carbon. To understand why this is happening, however, we need to start from a simpler beginning. A carbocation can be defined as any carbon chain where a positive charge exists on one of the carbons. The carbon with the positive charge has an empty p orbital, which forces the carbon to adopt an sp2 configuration. This is the reason its remaining bonds are splayed out flat, like the points of a triangle. But how do carbon chains acquire a positive charge to begin with? Well, there are many ways, and you will encounter them throughout your study of organic chemistry. The simplest way is shown here, in which a good leaving group, in this case chlorine, snaps off and takes its electrons with it. In doing so, it carries a negative charge away and leaves a positive charge behind on the carbon it was attached to. Regardless of how they are made, not all positively charged carbons are created equal. Their stability depends on how many other carbons they are attached to. Tertiary carbons are the most stable, followed by secondary carbons, and then primary carbons. Methyl carbocations are highly unstable. The reason for this bizarre stability behavior is due to a phenomenon known as hyperconjugation, where nearby bonds to hydrogens become attracted to the positive charge. These bonds bend inward to share some of their electrons. For a positively charged tertiary carbon, there are as many as 3 of such bonds nearby, allowing it to have the most electron donation, and therefore the most stability. Watch what happens as we remove the number of available neighboring hydrogens. The remaining hydrogens get pulled even closer to the positive charge. When we take thermal energy into consideration, something highly unusual takes place. Hydrogens sometimes swap places with the positive charge, a process called hydride shifts. Methyl groups and alkyl chains can also do a similar trick, but we'll be exploring that in a separate video. The difference in stability between primary, secondary, and tertiary carbons, along with the hydride shift phenomenon, leads to a general rule in organic chemistry, which we can watch here. The positively charged primary carbon will swap charge with the nearby secondary carbon, and then this will eventually swap with the tertiary. The movement of hydrogens essentially flows from the crowded centers toward the ends of the carbon chains, so that the positive charge can end up on the tertiary carbon. It is absolutely critical to understand the statistical nature of this process, though. Even though tertiary carbons are the most stable, thermal energy is causing molecules to jostle about and move rather chaotically. At any moment, a stable tertiary carbocation might shift back to a less stable secondary or primary, and then back again. Therefore, to fully appreciate the nature of carbocation stability, we have to view populations of molecules. Here we have 100 similar molecules. Notice how over time, more and more begin to convert into the green, stable tertiary state. At any given instant, one green might switch to a yellow or to a red, but even so, another will be switching back to green. At equilibrium, a disproportional number of molecules will be in the tertiary state. In this simulation, the equilibrium state gives somewhere between 50 and 60% as tertiary, denoted by the bottom left number. This does not necessarily represent the proportions that an actual solution of these molecules would adopt. It's merely the result of the current settings on my simulator, but it serves to outline the general principle that carbocation rearrangement tends to lead to tertiary carbocations. This chaotic movement of hydrogens and migration of positive charge might lead one to believe that a solution of carbocations are doomed to continue to shift from now until eternity. Take the molecule here, for instance. This is our original hexyl carbocation, shifting and twisting and moving without rest. Where does it end? Will the charge just keep bouncing around forever? The answer to this, thankfully, is no. There are a number of processes that bring this bizarre rearrangement to a close. The simplest of these is the end step of the E1 mechanism, which we'll explore in a later video. Other stops to the carbocation rearrangement phenomenon will be studied as they arise.